Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into something that's been buzzing around the scientific community, and that's the evaluation of engineering artificial general intelligence, or AGI.
Yeah, it's a huge topic, and I think, frankly, it's the topic. I mean, for decades, it was just a science fiction dream, but now, well, now it feels like we're actually on the cusp of something real. I think the recent advancements in deep learning are a clear indication that AGI is within our grasp.
I'm a bit more skeptical, honestly. Deep learning has definitely shown promise in specific areas, but I think equating that with AGI is a bit of a stretch. It's good at pattern recognition, sure, but can it reason? Can it truly understand?
I'm with you, Sarah, to some extent. Deep learning is brute force. It works, but it's not elegant. I think the real key to AGI lies in understanding how the brain handles spatiotemporal information and how it translates between different coordinate representations. That's something current deep learning models completely miss.
That's a really interesting point, Donald, about spatiotemporal reasoning. I mean, consider how effortlessly we navigate the world, understand spatial relationships. Deep learning struggles with that. It needs massive data sets just to perform simple tasks that a toddler can do.
But look at the advances we've seen. Large language models like GPT-4 can generate coherent text, translate languages, even write code. Isn't that a sign that we're on the right track? Just keep scaling up the networks and feeding them more data, and we'll eventually reach AGI.
See, that's where I disagree. I think that's just creating a sophisticated parrot. It's mimicking intelligence, not actually possessing it. AGI needs to be able to reason, plan, and generalize beyond its training data. It needs to be able to understand cause and effect and form abstract concepts. Deep learning struggles with all of that.
Exactly. Think about the self-driving car problem. They're getting better, sure, but they still struggle with unexpected situations, with generalizing to new environments. That's because they lack the ability to truly understand the spatial relationships around them, to translate between different viewpoints, and to anticipate what might happen next based on an understanding of physics and human behavior. Current systems are glorified pattern matchers.
So if we're thinking about evaluating AGI, what metrics are we even using? Is it just about performance on specific tasks, like image recognition or language translation? Or do we need to think about something more fundamental?
Well, performance is a big part of it, obviously. If an AI can consistently outperform humans on a wide range of tasks, that's a strong indicator of AGI. But it also needs to be able to learn new tasks quickly and efficiently, to adapt to changing environments, to demonstrate creativity and problem-solving skills.
And crucially, it needs to be able to explain its reasoning. A black box that gives you the right answer is not AGI. AGI needs to be transparent, accountable, and able to justify its decisions. We need to understand why it's making the choices it is.
Right. And that gets back to the coordinate representation problem. If an AI can't explain how it's transforming information from one coordinate system to another, how can we trust its decisions, especially in safety-critical applications? Imagine a self-driving car making a split-second decision based on some internal representation that we can't understand. Terrifying.
So how do we bridge that gap? How do we move beyond the black box and create AI that's both intelligent and understandable? I mean, looking at the brain, it's clear that there are hierarchical structures, distributed processing. It's not just one giant neural network. We're missing something fundamental about its architecture, I think.
I think we're getting closer to understanding the brain's architecture. We're developing more sophisticated neural network architectures that mimic some of its features, like convolutional neural networks that are inspired by the visual cortex. And with more data and compute, we can continue to refine these models until they achieve true AGI.
But those are still just mimicking the structure, not the function. We need to understand how the brain encodes and represents knowledge, how it performs symbolic reasoning. We need neuro-symbolic algorithms that combine the strengths of both neural networks and symbolic AI.
Yeah, I agree. We need to start thinking about algorithms that can explicitly represent spatial relationships and transformations. Maybe something inspired by the hippocampus and its role in spatial navigation. Imagine an AI that can build a mental map of its environment and use that map to reason about how to get from point A to point B. That's true intelligence.
That's fascinating, Donald. So how do we even start to translate that into an algorithm? Are we talking about completely new programming paradigms?
Potentially. I think we need to look beyond the standard deep learning frameworks and explore new ways of representing and manipulating spatiotemporal data. maybe something based on geometric algebra or topological data analysis. The key is to find a way to encode spatial relationships in a way that's both computationally efficient and semantically meaningful.
But those approaches are often very specialized and don't generalize well to other tasks. Deep learning, on the other hand, is much more versatile. You can train a deep learning model to perform a wide range of tasks just by feeding it different data.
But that versatility comes at a cost. Deep learning models are notoriously data hungry and lack the ability to generalize beyond their training data. Neurosymbolic algorithms, on the other hand, can learn from much smaller datasets and are much better at generalizing to new situations. They're also more transparent and explainable.
It's interesting. One could argue we need to better define the problem before we can say what the solution is. AGI is such a broad term. What about focusing on specific cognitive abilities like reasoning, planning, or understanding natural language, and then trying to build AI systems that excel at those specific tasks?
And that's essentially what we're doing with deep learning. We're building AI systems that are really good at specific tasks, and then we're gradually combining those systems to create more general-purpose AI. It's an incremental approach, but I think it's the most practical way to achieve AGI.
But that incremental approach might be leading us down a dead end. We might be creating a collection of specialized AI systems that don't truly understand the world around them. We need to focus on building AI systems that have a deep, fundamental understanding of the world, that can reason about cause and effect, and that can generalize to new situations.
And that requires a different kind of algorithm, one that can explicitly represent spatial relationships and transformations. We need to stop thinking about AI as just a pattern recognition engine and start thinking about it as a system that can build a mental model of the world and use that model to reason about its environment.
So let's get practical. What are some specific research directions that we should be pursuing to make progress on this? From a neuroscience perspective, I'm intrigued by recent studies on neuroplasticity in the hippocampus. Could understanding how synapses change and adapt to new environments inspire novel learning algorithms for AI?
From a deep learning perspective, I think we need to focus on developing more efficient and scalable architectures. We need to find ways to train larger models with less data and less compute. And we need to develop better ways to regularize these models to prevent overfitting.
From a neurosymbolic perspective, I think we need to focus on developing algorithms that can seamlessly integrate neural networks and symbolic AI. We need to find ways to represent knowledge in a way that's both computationally efficient and semantically meaningful. And we need to develop better ways to reason about that knowledge.
From a spatiotemporal perspective, I think we need to focus on developing algorithms that can explicitly represent spatial relationships and transformations. We need to understand how the brain handles different coordinate systems and develop algorithms that can mimic that ability. And we need to develop better ways to visualize and interpret spatiotemporal data.
That's great, guys. It sounds like there's a lot of exciting work to be done. It seems we're all advocating for more biologically inspired approaches in different ways. It seems like understanding the brain is key, but whether that translates to pure imitation or using it as inspiration for new algorithms is the real question.
Absolutely. And I think the future of AGI is going to involve a combination of all these approaches. We're going to need deep learning, neurosymbolic AI, and spatiotemporal reasoning to create truly intelligent machines. The scale of the compute needed just makes that more and more obvious.
But I think we need to also address the ethical implications of AGI. As we create more intelligent machines, we need to make sure that they're aligned with our values and that they're used for good. The potential for misuse is enormous.
Definitely. And the coordinate representation problem is particularly relevant here. If we don't understand how an AI is making its decisions, we can't be sure that it's not biased or making decisions that are harmful to society. That understanding how the system makes decisions is critical, and it is not just about performance metrics.
That is so true, and that is one of the critical elements in creating an AI system that we can trust. The transparency of coordinate representation is fundamental. We need to understand how the AI is interpreting and interacting with the world around it. The question of trust is important to make sure that what we build is in accordance with human values.
We have come a long way, but we are not there yet.
Agreed. With that, let's talk about what research topics would be of interest. This is the direction that I find very interesting right now. How can we develop algorithms that integrate spatial reasoning with other cognitive functions, such as language understanding and planning? This is very important for developing a better AI model.
That's a great direction. My research attention has been focused on How can we design algorithms that can effectively translate between different coordinate systems, for example, Cartesian, polar, geographic, to allow agents to reason about spatial relationships in a more nuanced and integrated manner?
I find the interplay between neuroplasticity, as observed in the brain, and the dynamic adaptation mechanisms required for complex AI agents is fascinating. Perhaps simulating specific neuronal pathways and synaptic interactions could lead to more robust and adaptable AI agents, mirroring the flexibility of the biological system. How do you all think of that?
I agree. I think those biological questions can be the start of answering fundamental computational questions of intelligence. How can we quantitatively measure the sophistication of increasingly sophisticated neural network architectures? Is there a direct correlation between increasing depth and complexity of a neural network and its ability to mimic or approach actual human intelligence?
Well, thank you all for this enlightening discussion. It's clear that the path to AGI is complex and multifaceted. It's not just about brute force, it's about understanding the fundamental principles of intelligence, both biological and artificial. Join us next week as we dive into the latest research on consciousness and the hard problem of subjective experience. Until then, keep exploring.